There's a fascinating lever paradox from Steve Mould. Check it out if you haven't done so already. The paradox has to do with these two levers. The first has equal arms and carries 1 kilogram, while the other instead holds half the weight at twice the distance from the pivot. Because you've halved the mass but doubled the distance, the finger holding it requires exactly the same force. Steve then reasons that the two experiences are identical from the finger's point of view, and that there's no experiment that would be able to distinguish them. But if you've watched his video, you'll know that he discovers that this is wrong, which raises the question of why the intuition felt so right. In this video, I want to dig into all of this. First, we'll break down why this is wrong and what actually happens. Next, we'll address why Steve's intuition seems very reasonable despite being incorrect, and relate it to the subtle difference between gravitational and inertial mass, a topic that took until Newton to recognize and until Einstein to actually prove. Finally, we ask the question of, if these experiences between the two levers are really different, then what actually makes them different? So let's get right into it.
Suppose I'm holding a mass. I know that if I doubled that force, then the thing would accelerate upwards at little g.
Now this is at the core of the paradox. So why is this really? Like, what is it about this intuition that's right? There are two conceptually different kinds of masses. The first is called gravitational mass, and it's just a ratio of the weight of an object to the gravitational field in which you place it. The second one is called inertial mass. It's another ratio, but this time it's of the force you apply to an object divided by the resulting acceleration. Now, it might sound like these two things are exactly the same, right? I mean, we're always told that mass is mass, and if you're in a gravitational field, the force is equal to mg. If you apply a force to an object, it's going to accelerate at a rate of that force divided by the mass. What's the difference? Well, experiments show that there really isn't a difference between inertial mass and gravitational mass. Now, even though in our universe, gravitational mass and inertial mass are the same thing, you can still imagine theoretically living in some universe where these two aren't the same. But let's get to the core of the paradox. Why does it feel so right intuitively that as long as the weight that I feel when I push on this lever is the same in two scenarios, that I'll also have the same experience in both of those scenarios?
And then I was thinking, like, is there a neat way, like, is there something I can point to and say, look, this is where it deviates from intuition?
Steve's paradox boils down to this simple fact that we've been taught since the beginning of our studies of physics. The inertial mass and the gravitational mass of an object are the same thing. And that's why this result feels wrong to us. Levers, when we push on it, we are feeling an experience of weight, and we are feeling an experience of inertia. But there's no reason for a lever that the resulting inertial mass and the resulting gravitational mass that's in the sensation of what we're feeling should be the same. So how do we make sense of this quantitatively, right? Well, okay, let's just consider a general, completely black box, right? And all we know is that it satisfies the principle of mechanical advantage. So you put a force in, there's like a string coming out of it or something, you put a force on it, and then you, at the output side, you get a force that's multiplied by the mechanical advantage. Let's call that S. So there's some multiplier, and we know that the force that we get out is equal to S times the force we put in. And then similarly, but opposite, the displacement on the output, X out, is going to be X in divided by S. That's the way levers and pulleys and all that stuff works. Also notice that the velocity has exactly the same rule as the displacement. So the output velocity is going to be the input velocity divided by S. And the output acceleration is going to be the input acceleration divided by S. Okay, great. So now let's look at the mass. What are the sum of the forces on it? It has weight, it has its mg, and then also has the force that's coming from the output of our lever, which is the force that's been multiplied by s. They have to equal the mass of that object times its acceleration. But we saw earlier that the acceleration, the output acceleration, is equal to the input acceleration divided by s. So writing down that equation and rearranging a little bit, look at this. We see that the form that we end up with looks exactly like Newton's second law, but where the gravitational mass is not necessarily the same as the inertial mass. In fact, the gravitational mass is just the actual mass on the output side divided by the mechanical advantage. And the inertial mass is that mass on the output side divided by the mechanical advantage squared. Amazing, right? It means any lever, any pulley, the experience you feel is identical to the experience you'd feel pushing on an object in a universe where gravitational and inertial mass are different. It's crazy. That's exactly what it would feel like. We just derived these equations by imagining that gravity was the source of the force, so that we could come to terms with our intuition about masses. But this force could really be from anything, not just gravity. With this interpretation, the gravitational mass equation instead becomes a force equation, so there's no longer a need to distinguish between different kinds of mass. I should mention here that by W, I mean the force required at the input to hold it still, which I'll refer to as perceived weight, despite that gravity need not be the driver here if something else is causing F out. It's also exactly the intuitive result we know for how levers multiply forces. Similarly, I'll refer to M as the perceived mass at the input. When Steve initially started thinking about these levers, he thought maybe it had to do with the fact that rotating things are weird.
And I thought, well, it's because it's a spinning thing. The physics of spinning things is counterintuitive. But then I was talking to Henry from Minute Physics about it, and now I think I'm wrong.
But actually, thinking of the problem rotationally is another perfectly valid way to work out the problem. Look at this. Here are the equations for the perceived weight and the perceived mass. This means we can move forces and masses around all we like without changing the physics, as long as we appropriately scale them to keep these two perceived quantities the same. For our lever, the mechanical advantage S is equal to the ratio of R in to R out. And actually, to be pedantic, it's the negative of this, since opposite ends of the lever move in opposite directions. Plugging this in while keeping our perceived weight and mass the same, we see that the relationship we need is that R out times F out is constant, and M out times R out squared is constant. You may recognize the first equation as torque and the second one as the moment of inertia. And here lies the answer to our riddle. Steve's experience of the finger involves not just the weight felt at a known distance, or torque, but also the mass felt at a known distance, or moment of inertia. So in order to keep the experience the same as we adjust the output radius, we need to scale the weight of the object by 1 over r, as expected, but the mass by 1 over r squared. This second part didn't happen in Steve's original paradox, which is why we got the wrong answer. One more useful tidbit. What happens to kinetic energy? Well, it's 1/2 mv squared. M scales as inverse r squared, while v squared scales as r squared. These two exactly cancel, meaning that the kinetic energy doesn't change at all as we make our adjustments to the lever. In fact, this gives us a really nifty way to do analysis on levers. Rather than try to think of both sides of the lever at the same time, we can just push everything around at our convenience according to this recipe. Let's try applying this reasoning to Steve's second lever. It involved a mass of 1/2 kilogram at twice the distance from the pivot. If we just slide that mass to the left, while simultaneously making it larger as we go, as the inverse square of the distance to the pivot, we keep the physics exactly the same. We can even keep going right through the pivot, all the way to the other end, where the radius is halved, so the mass needs to be quadrupled, turning it into 2 kilograms. At this point, we've basically eliminated the lever altogether. It's just a finger pushing directly on a mass, with no more lever funny business. When we apply a 1 Newton force over a distance of 1 meter, we do 1 joule of work on our virtual mass, giving it a kinetic energy of 1 joule. Now, when we push the virtual mass back across the pivot point to its original location, we found that its kinetic energy doesn't change through this transformation. So the final kinetic energy remains 1 joule, as expected, and the paradox has evaporated. In closing, the failure of intuition here is understandable, given the fact that both gravitational mass and inertial mass have the same letter M. After all, one of the first things we learn while studying physics is that increasing mass both makes it heavier and harder to move in exactly the same way. There's no practical reason to distinguish them in our universe, and as a result, this has become deeply ingrained in our intuition to the point that we may incorrectly apply this equivalence not just to simple masses, but also to inapplicable systems without even realizing it. So let this be a lesson. Intuition can help us make discoveries, but when we use intuition to take shortcuts, we can sometimes arrive at an incorrect answer. I hope you enjoy this thought experiment, and thanks for watching.